Welcome to 8.2 lesson on products and quotients of functions. This is example 1. We are going to let f of x equal x plus 3 and g of x equal x squared plus 8x plus 15. So we have here two functions, and we are going to take the product of them in A, and in B we are going to take the quotient. These are called component functions, and the y that we are left with is going to be the composite function. So for A, our goal is to find the graph y equals f of x times g of x. So the product of f of x and g of x. And all I really need to do is sub those in. So f of x is x plus 3, g of x is x squared plus 8x plus 15. And now I need to use my distributive property. I need to distribute the binomial with the trinomial with the quadratic here. So I have x times x squared equals x cubed. X times 8x is 8x squared. X times 15 is 15x. Now multiplying by the second term of the binomial, multiplying by 3, we have 3x squared plus 24x plus 45. 3 times 15 is 45. So at this point, we would group our like terms. We have an x squared here and an x squared term here, and then we have an x term and an x term, and the rest are on their own. So we have x cubed plus 11x squared plus 39x plus 45. So this is our new function. This is y. Y equals x cubed plus 11x squared plus 39x plus 45. But in order to graph this, it looks pretty difficult to graph. So I'm going to use the fact that g of x, that's this guy up here, g of x can be factored. And so that's going to help us graph this. So this is the function. And then in order to help graph, I'm going to rewrite this step. But instead of distributing here, I'm going to factor g of x. And it'll make sense in a second. Y equals x plus 3. That's f of x. And now g of x factored, I need two numbers whose sum is 8 and whose product is 15. Well, that's positive 5 and positive 3. So I have x plus 3 and x plus 5. And now I can see that I have two terms here, two binomials that are the same. So I have x plus 3 squared times x plus 5. And using the information that we have from both of these equations, we should be able to draw a fairly accurate graph. Okay, so the first thing I can identify from our factored form is the zeros of the graph. So we have y equals x plus 3 squared times x plus 5. So here there are zeros at x equals negative 3 and x equals negative 5. But we know also that because this first binomial is squared, that this is a second degree zero. So this is a zero of second degree, which means that it is simply going to touch the x-axis without crossing through it. And negative 5 here is a first degree, which means it is going to cross the x-axis at negative 5. From standard form, that was y equals x cubed plus 11x squared plus 39x plus 45. We learn that the y-intercept is 45. Okay, so we have our zeros, which are our x-intercepts, and we have our y-intercept. We also know that this is a cubic. The highest power here is a cubic, so it's going to take something, it's a positive cubic, so it's going to be something like that, or like this. Somehow it's going to start down here in the bottom and do one weave and get to the top. So we'll see what happens. -1, -2, -3, -4, -5. So we said at -5, it's a first degree. It's going to cross over 1, 2, 3, 4, 5. It's going to cross the x-axis at -5. And it's going to touch the x-axis at -3. And then we have our y-intercept at 45. So I'm just going to go 10, 20, 30, 40, 50. There's 45. That's the point, 0, 45. And we're ready to draw. So I'm somehow coming up from the bottom. I'm crossing at -5. I need to come back down and touch at -3, and then go all the way up to our y-intercept at 45. And that is a basic sketch of the cubic y equals x cubed plus 11x squared plus 39x plus 45, which is a composite function, f of x times g of x. Okay, because there are no restrictions on the original two functions, so maybe I'll write my original two functions. We need to talk about restrictions here. We can see from the graph that there aren't going to be any restrictions. But because there are no restrictions on f of x and g of x, there are no restrictions on x or y. So domain is x element of the real, x of the real numbers, and range also is y of all real numbers with no restrictions. Okay, example 1b, we have the same two original functions, f of x equals x plus 3, and g of x equals x squared plus 8x plus 15, and we are asked to find y equals f of x over g of x. And so our first step is to sub in our functions, x plus 3 over x squared plus 8x plus 15. Now, one of the steps in part A helped us to see that this denominator here, the function in the denominator, could be factored. And we've already done the work to factor it. So I'm just going to substitute what we got in A. It was equivalent to x plus 3 times x plus 5. Now we can cross out x plus 3 over x plus 3 because that equals 1. And we're left with 1 over x plus 5. And the restriction on this that we can write here, the restriction, one of the restrictions is that x can't be 5, but we've also already learned, because x plus 3 is included in the original denominator, that x cannot equal -3. So out here we put the restriction where the information for this restriction is not included in the simplified function. So we make sure to note it. This is a rational function, and a sketch can be produced by applying a horizontal translation to the function y equals 1 over x. So we'll try to sketch our graph, and maybe I can even just do it off to the side here. I'll go to this side. Okay. I'll draw y equals 1 over x in red. And then we will apply a horizontal translation to that graph to get our graph. So this goes through the point 1, 1, and it just comes down close with an asymptote at x equals 0 and one at y equals 0. And same thing in quadrant 3. That is the graph of y equals 1 over x. Now we apply a horizontal translation to this, 5 to the left. So we're going to head down to -5 for our asymptote. 1, 2, 3, 4, 5. We're going to have an asymptote here rather than at x equals 0. And we will use blue for the graph of y equals 1 over x plus 5. It's going to come down by its asymptote and curl along and carry on to positive infinity. And same thing, it's going to carry on to negative infinity. But we're still missing one step. We said that there was a restriction on this function that x could not equal -3. So we need to find -3, and we see nothing's really happening there, but we've learned in an earlier unit that this is going to be a gap. There's a hole at x equals -3. So we identify that by an open circle. Whenever you need to find the restrictions on a function, on a composite function, you need to head back to the two original functions, the component functions, and use the restrictions on this and the restrictions on this when we have put it in quotient form as it asked us to do. So this function is undefined for x equals -3 and x equals -5. Therefore, the domain x belongs to the set of real numbers, but x cannot equal -3 and x cannot equal -5. And for the range, we can see that there is an asymptote at y equals 0. So for the range, y belongs to the set of real numbers, and y cannot equal 0. There's another place where there's a restriction on y. So this gap occurs at x equals -3. If we sub x equals -3 into here, x equals -3, we will get 1 over -3 plus 5, which equals 1 over 2, which is a half. So this hole right here is at -3 positive a half, which tells us the restriction on the range is y cannot equal 0 and y cannot equal 1/2. In example 2, it is about baseball marketing. So in an effort to boost fan support, owners of a baseball team have agreed to gradually reduce ticket prices. So P here is price with respect to the game, per game. So G is the number of games that have been played so far this year, and P is the function that will show how they're going to reduce the tickets. So each game, the tickets are going to be reduced by 10 cents. So $25 for game 0, $24.90 for game 1, $24.80 for game 2, etc. throughout the season. So the tickets are getting a little bit cheaper from each game to the next. They've also decided to give away caps at each game according to this formula. In hundreds of caps, 2 minus 0.04 times the number of games. So at the first game, they're giving away 196 because this is in hundreds. Second game, they're giving away 192. Third game, they're giving away 188, and so on and so on. So the first game that they give out hats, they're giving away the most hats, and in subsequent games, they're giving away fewer hats. And then we also have a function n here. This is showing the number of fans that are coming to games since they began these two marketing strategies. So n is the number of fans that come to the games since the marketing strategies have been employed, and this is in the hundreds. Okay, so caps, this is measured in hundreds, and the number of fans is measured in hundreds. And we have a composite function here, f of g. It is equal to p of g times n of g. And we need to simply figure out, before sketching a graph, what does that mean? What does p of g times n of g represent? So p is going to be the price per ticket, and we're going to multiply it by the number of people in the stadium. So it'll be the total money that's coming in, which is called revenue. So f of g, which equals p of g times n of g, represents the revenue. Revenue is the money coming in. Good. So the question that we need to answer is, will the owners increase or decrease their revenue from ticket sales under the current marketing plan? So this is their current marketing plan. Will that marketing plan increase or decrease revenue? Well, let's figure it out. So we're going to multiply p of g by n of g to produce the combined function f of g. So here we go. We're going to sub in for p of g. This is going to be equal to 25 minus 0.1 g. And n of g is 10 plus 0.2 g. And if we distribute these, we have 25 times 10 is 250. 25 times 0.2 g is 1/5 of 25. So that's plus 5g. And then we have inside times inside, which is negative 0.1 times 10, which is negative 1g. And then negative 0.1g plus, times positive 0.2g. That's negative 0.02g squared. Now we can group like terms. We have and rearrange so that our squared, our highest ordered term is in front. We've got negative 0.02g squared plus 4g plus 250. So then we would be required to graph this function. Okay, so there's the graph of our composite function. We only had to do for g greater than or equal to 0 because we can't have negative number of games. So this combined function is the product of the ticket price and the number of fans attending in hundreds. Therefore, f of g equals p of g times n of g represents the revenue from ticket sales in hundreds of dollars. Note that the function is quadratic. It increases until about game 100 and then decreases after that. So the owners will increase their revenue from ticket sales in the short term under their current marketing strategy, but eventually this strategy will no longer be effective. Again, a typical Major League Baseball season is 162 days, 162 games long, so it looks like they have a good idea here. B of example 2 gives us the same baseball team with the same marketing schedule, marketing strategy, and asks us to find out or decide what this function means. F of g is a composite function, C of g divided by N of g. So remember, C of g is the number of caps being distributed at any given game, and N of g is the number of people at any given game. So what does this function, F of g, represent? Yeah, exactly. It's the proportion of people who will receive a cap. It's the ratio of caps to people. So the question that we need to ask is, how likely are you to receive a free baseball cap if you attend game 5? There's a couple different ways to do this. One of them, well, they both start, and we're just going to do the pen and paper method. But they both start with simply subbing in our component functions. We have C of g, which is 2 minus 0.04 g, measured in hundreds. That's the number of caps, over the number of people, also measured in hundreds, 10 plus 0.2 g. Now, one way to do this would be punch these into the calculator as a single function and find out, what the y value is at game 5. The other way to do this is simply sub in 5 into our equation, which is what we will do. So we have g equals 5. We want to know the likelihood of getting a cap at the 5th game. We have 2 minus 0.04 times 5 over 10 plus 0.2 times 5. 0.04 times 5 is 0.2. So this reduces to the top, the numerator there reduces to 1.8. And 0.2 times 5 is 1. So 10 plus 1 is 11. And if we put this ratio into our calculator, it will come out with 0.16333, and the 3's will repeat, which tells us that, according to the equation, there is about a 16% chance of receiving a free ball cap at game 5. And this is one of many applications of product and quotients of functions. 8.2 homework is found on page 435, numbers 1 through 11, 13, and 14.